Hello everyone, my name is Po Junkang. Today I'm going to present our paper, Radar Occupancy Prediction with Lidar Supervision, while preserving long-range sensing and penetrating capabilities. The motivation of this work is to classify free and occupied space in noisy radar images. To achieve radar occupancy prediction, we train a UNet network with Lidar supervision. This is because Lidar provides more precise measurement with less noise. However, there are still several challenges remaining. The first challenge is that radar sensing range can be limited by Lidar, because Lidar has a shorter sensing range compared to radar. After leveraging Lidar's supervision, the radar long-range sensing property is degenerated by Lidar. The second challenge is that some objects are only visible to Lidar. For example, objects like slim tree branches and twigs are visible to Lidar but invisible to radar. We found that if we use Lidar data as training ground truth directly, the trained network not only fails to detect radar invisible objects, but also tends to make false positive detection. Next, the third challenge is that Lidar does not have penetrating capability. For example, there are some objects and vehicles behind a hedge and street corner to the left of the eagle vehicle. They are visible in radar image but occluded in camera image and Lidar scan. Therefore, if we leverage Lidar supervision directly, the trained network will fail to preserve radar penetrating capability. Now, let's talk about our method. First of all, to handle the radar invisible issue, we propose training data preprocessing to remove radar invisible measurements from Lidar scans. After the training data preprocessing, the network is not forced to detect radar invisible objects and make least false positive detection. To preserve long-range sensing capability, we simply extend a near-range trained network to long-range inference. An interesting question here is which coordinate space could lead to better performance, Cartesian space or polar space. After the experiment, we found that the network trained in Cartesian space fails to detect objects outside training region, while the polar space network works well. We also found the polar space performs 4.2 times better IOU than Cartesian space on extending near-range training to long-range inference. We suggest this is because the data dissimilarity between near-range and long-range data in Cartesian space is blur and shape change, but in polar space is only scale change in angle axis, and UNet is more resilient to scale change than shape change. To preserve radar penetrating capability, we propose the sliding window inference. Instead of inference the whole radar image directly, we do inference on image segments, then combine the inference results together. For example, we use blue region as network input, and the inference result is shown on the right. In this case, radar penetrating capability degenerates. However, if we shift the inference region a little bit, the originally occluded measurements become non-occluded measurement from the network's perspective. Therefore, the network successfully predicts occluded measurements and preserves the radar penetrating capability. In summary, our method can preserve penetrating capability and detect moving objects outside Lidar sensing range. Thank you for your attention, and please refer to our paper and demo video for more information.